We've been doing a lot of calculations in the class, but I do want to emphasize at the start of class today that math is more than just calculations. It also can involve doing exploration, experimentation, making conjectures. In fact, we'll do that in a couple places today. One here initially, I want to just show you some pictures that are nice and pretty. And then secondly, when we do the numerical integration and talk about the meaning of ultimately the midpoint rule and Simpson's rule, that we can experiment to help us understand better. Anyway, to show you what I want to show you visually today is let's go ahead and look at the Lissajous figure example again, except this time I'm going to define my functions involving a parameter. F sub A, let's call it, of t is going to be my x coordinate. What's the A? The A is just an example of a parameter that I want to give myself the flexibility to change if I want. Why? Because I feel like it. And maybe it's useful. And it's going to be the multiplier of the t inside the cosine function. Last Friday, A was 3. I'll pick the g of t to be sine of 5t again. R is going to be the position vector. I'll call it R sub A of t. It's going to depend on A still. Notice in the using the subscript here, I am treating A like a variable because I'm putting an underscore after it here and here when I'm first defining these functions, just like the variable inside the square brackets. But once I've defined the function, then don't use the underscore anymore. And let's go ahead and do the velocity vector too. That's just going to be the derivative of the position vector. I'm just going to put a prime in here. And I'm also interested in seeing what is the formula for the velocity vector so that I can also figure out the speed. What is the formula for the velocity vector? There it is. Oops. A must be something specific. I need to clear it out. Clear A. There we go. That's the velocity vector. The x coordinate depends on A. And that means the speed depends on A as well. Let's use a subscript for that too. Speed sub A of t is the square root of this thing squared. Plus this thing squared. Right? This is stuff I've taught you about. The speed is the length of the velocity vector, which means take the first component and square it plus the second component and square it. Something you should know for exam 1. You don't need to know this Mathematica code for exam 1, as in this example, though you should understand the bigger idea about, like with functions, when you first define them, put the variable inside the square brackets and use an underscore. You should know that for the exam. Don't worry about the subscripts for the exam. I will not put those in the exam. And I can also do the distance traveled. Dist sub A of t. Use the n integrate again because it's got to do numerical integration. It's too hard to do symbolic integration. You have to do approximations. That's why. Tau in here. Tau goes from 0 to t. Everything's set up now that I should be able to make graphs that can change as I change A. I could also change time as well. I showed you that before. But let's focus on just what happens as A changes. The function I want to graph here is the parametric curve. That's the R. R sub A of t. I'll use a tau here. Tau goes from 0 to t. Let's make it, say, red. And we need a plot range here so we can see it well. last Friday, again, A was 3, but I want to allow myself to change A, and this is the syntax for how to do that. This syntax will have A start at a value of 3. I'll have a slider that'll allow me to lower A to as low as 0.1 or increase A as high as 10. And hopefully not get mistakes. Let's see. Well, oh, we also need, I need to use a 2 pi here. Excuse me, not a t. That's why. Okay. And so what we see now here is the Lissajous figure. But now I'm not thinking about motion anymore. I could. Instead, I'm going to think about what happens as A changes. And so I can move the slider to see what happens as A changes. And it's kind of pretty. And sometimes it's fairly mundane, like that one, though still interesting. And sometimes it's a lot more interesting in terms of being kind of wilder all over the place. So this can lead you to make conjectures about how the value of A affects the graph and why it's simple in some circumstances. A is close to 5 there. Why is it so simple? Because 5 matches the 5 there. That's why. You could also make graphs of the speed and distance traveled. Let's just do the speed because I think the distance traveled would take too much computational time. An ordinary plot of the speed and see how A affects things. Except I need to put it inside manipulate again. I will eventually test you on understanding the syntax, but for the moment I'm not. That's a graph of the speed as a function of time. And again, we're interested in seeing what happens as A changes. Does anything interesting happen? Well, kind of. Oh, yeah, some interesting things happen there. Wow, look at that. Let's see. That's pretty wild. Sometimes it seems to be periodic, and here it seems like maybe it's not periodic. It seems like it keeps increasing. Is that just a figment of my imagination, or is the plotting window not big enough? I'd have to test that conjecture by making a bigger plotting window. I won't take the time to do that, but at the moment, we can say it's a pretty interesting kind of thing. Here it's almost close to constant. That must be close to when A is 5. Yeah, when A equals 5, it is actually constant. That's the circle case. Circular motion at a constant speed. So you can make conjectures in math. You can do experiments and you can make conjectures. And that's my entire point that I'm trying to make with all this, is that interesting things can be experimented with and conjectures can be made. Doesn't mean you can necessarily prove your conjecture, but you can make conjectures. And your conjecture could be right or it could be wrong.